All right. Good evening, everyone. Let's get cracking. We have quite a bit to get through today. Okay. This is where we stopped yesterday. All right. I asked you to go through this question. Did anyone have a difficulty with this? It's all right. So silence means no. Okay. So the currents that we calculated, I1 and I2, 21.04, 147.755 milliamperes. Of course, once you have those currents, then you can find V1, V2, and the power that was required, etc. So I'm not going to spend much time going through that. Okay, so let's pick it up at question 3. I gave you these questions. I asked you to look at them as we would be going through them today. So for part A, Mr. Thompson, you want to start us off with this one? What are the considerations? What's the information you're given here? What's the important information you're given that will guide you to a solution?
First, I consider that you mentioned that it's a characteristic impedance, and we have two 6K resistors and one 4K resistor. So from that, I interpreted that it would be a pi network with the two 6K resistors at the two terminals and the 4K in the middle.
Okay, so in other words, you're saying that it needs to be symmetrical.
Yes, sir.
Okay. So for a symmetrical network, so that's 6K, 6K, 4K. Mr. Thompson, continuing, you're told it's terminated in its characteristic impedance.
Yes, sir.
So where do we go from here?
Sir, I use the formula for the output impedance for a symmetrical pi network being Z output impedance equals the impedance.
Characteristic impedance.
Oh, yes, sir. The characteristic impedance is equal to the square root of the 4K times, it would be the Z 4K.
I'm listening.
Times 6K squared over.
All right. Generally, Z short circuit times Z open circuit.
Yes, sir.
All right. So for this network, what would be the short circuit impedance?
So you would consider the short circuit of the port 2, so that would take out the 6K and you would have 6 in parallel with the 4.
Okay. So that gives us 24 over 10. And for the open circuit?
And for the open circuit of port 2, you would have the 6 in parallel with the 4 plus the 6K.
Okay, so that would be 60 over 16 over 16.
Yes, sir.
Them long formula that you were giving me, yeah. All right. So we simplify this.
Yes, sir.
Sir, question.
So this gives us 9K, right? With your formula, did you get the same thing? Is it 9K?
Oh, I would, after that, would you find the square root and then you would get 3K.
Got 3, sir.
All right, so that's 3K.
Yes, sir.
Uh-huh. So I have 3K?
Yes, sir.
Okay. So where do we go from, where do we go from here?
Sir,
You'd find the
you
total
would
current.
consider finding the individual, the matrix.
Why? What did the question ask you for?
Sir, ask for the power, given that the
For what?
power supplied to the network. Yes, sir.
Okay. Mm-hmm.
A 15 volt source.
So where do we go from here?
Sir, you would need,
Sir, go
you
find
would
the
need to
total
attach the
current.
15 volt source.
Go again?
You would consider the 15 volt sources at the port.
All right, so we have 15 volts. Uh-huh. And?
To find the power, you would need the current through the entire network. So, or you could use I equals YV to determine the current.
Yeah, so tell me what I need to do from it. How do I go about doing that?
All right, sir, you would need to find the admittance. So I'm not, I didn't reach that far, sir, but what I was
Maybe you
doing is
didn't
to
reach
find
that
the
far.
current.
This is the first question. So you didn't do any of the others?
No, sir, I was just doing this one, sir.
Oh, Jesus. All right, anybody else?
May I answer?
Yeah, man, go ahead.
Given that we find the characteristic impedance to be 3K,
Mm-hmm.
I would have used that, and the voltage supply to find the current it should have been I1. So V1 would be
All right, Mr. Blackwood, I'm going to stop you right there.
Yes, sir.
Why do you need to find the current?
Because to find the power, I would need the current and the voltage.
What did the question ask you for?
The power delivered to the network.
What constitutes a network?
Sorry, oh, sorry, bye.
What constitutes a network, Mr. Blackwood?
The Z0 would be the impedance of the network. So V1, which is
Ask your questions. I said, what is the network made up of?
resistors. Sir.
Which ones? What? Which resistors?
I see 4K and 26K. Oh, we found the.
Is that the network? Read the question again, because maybe my English is really poor.
$15-volt source, given the network is terminated in its characteristic impedance.
Okay. So tell me now, what constitutes a network? Anybody, please help us. So back for the, as you were trying to.
Or the 15 volt source on
with 6K resistor and a 4K resistor.
What is, all right.
Sure, what I did was I placed 3K as the load, which is Z0. So the whole circuit is complete now with the 15 volt on the input side and the 3K on the output terminals.
All right. How will you go from there?
What I did was I found the admittance parameters.
But why? Why?
Sir.
Why? Tell me why.
No,
So
sir,
V square over Z.
because I was on the topic now, I realized that that wasn't really needed. So
All right, you found the parameters. What did you get for your final answer?
I'm so confident tonight.
What did you get for your final answer? I didn't ask your level of confidence. What did you get? Mr. Beckford, what answer did you get?
Sir, would it just be
Sir.
would you just square the voltage and divide by the resistance to the power?
Yeah, V square over R. You know.
Sir, it would be V squared over the characteristic impedance form. Because remember that would be the impedance seen by the network.
Thank you very much, Mr. Powell. This is what the 15 volt supply is feeding. Because it is terminated in this, it means that P is simply equal to V squared over Z, which is 15 squared over 3, which gives you 75 watts. This is the difference, students, when you say that an exam is long, but it is as short as your understanding of the theory. The fact that it is terminated in its characteristic impedance means that the impedance seen looking in is 3K. So
over Z and done.
Yeah, remember that one.
I'm just had enough of flow right now. Anyway, so what we're saying is that because you're terminated in Z0, because you're terminated in Z0, doesn't matter what the network is anymore. Z0 here is 3K. So it means that when you look in here, you're gonna be seeing 3K. That's 15. So you have 15 squared over 3, give you 75 watts. Looks like I'm going to get cut off again, but you know, so be it. You're then asked to arrange the resistors to form a T network. So with the T, again, it is still connected in its characteristic impedance. So we have the T. It means now that this is 6K, 6K, 4K. terminated in Z0. Find Z0, find the change in power. All right, so you want the percentage change in power delivered. Now we're good. So I suppose the fact that you hadn't moved from that first question means that you didn't get to this one either, yeah?
Yes, sir.
Yes, Mr. Hodges. Yes, Mr. Hodges.
Yes, sir. Sir. You hearing me?
Go ahead now.
Sir, are you hearing me?
Go on now.
I say yes. Okay,
Yeah.
so I've found using
I'm
first
not hearing you now.
principles to determine the admittance and the emitters. Since is everyone else hearing me?
Yeah, well, I hear you.
Yeah, man.
Yeah.
Go ahead, maybe it's just me.
Okay. So I found the Y parameters using nodal analysis, and I found the Y parameters. And given that we know that the impedance is equal to the Y inverse, well, capital Y parameters inverse, I found the impedance by that formula.
Right.
I wanted to think first principles is what we.
Yeah, but if it asks you to use first principles, where you understand that to mean? Sargis?
Principles, yes, sir, answered.
All right. Let me what's happening today? What the dickens is happening today? All right, let's move this up here. All right, so here we are now. Everybody seeing the screen? Because this internet thing is all over the place this evening.
Yes, sir.
Yes, sir. I see no screen, sir.
All right, so you're asked to do this from first principles, which means therefore that the first thing you need to do is to write your equations. I1, Y11, V1, 1, 2, V2, I2, 2, 1, V1, 2, 2, V2. And of course, for the impedance parameters, V1, Z11, I1, 1, 2, I2, V2, Z21, I1, Z22, I2. So this is the first thing that you're expected to do. All right? First thing you're expected to do. From there, you then, from your circuit, today seems that it's going to be a bust, but anyway, I will put on. So that's I1 over V1 with V2 being equal to 0. It means, therefore, gentlemen, that you're going to come back to your circuit, short circuit port 2, find the relationship between I1 and V1. V1 and I1 are connected by virtue of the impedance looking in, right? So you have 2 in series with 4, which is in parallel with 3 in series and 4 and 2, okay? So the impedance looking in, 2 in series with 4, which is in parallel with 3, which is in series, 4 in parallel with 2. I hope that is how it is. It is. Whatever this is equal to, yeah, you find, so where is it equal to? You know that V1 is equal to that impedance times I1, which implies, therefore, that Y11 is equal to 1 over the impedance. I'm not doing this for you, because you have to get to a point where you're able to do these things. If you can't do them, again, you're going to you're going to get 0 on this topic. So I'm not going to beat around the bush. I'm not going to do it for you, because you have to learn to do it. For Y21, V2 over, sorry. I2 over V1 with V2 being equal to 0. All right? You go back to your circuit. You know that I2 would be the current flowing here. Yes? So you're going to find the relationship between V1 and this current. Right? So you see, you would have had the resistance equation, right? What you're trying to find is the current through that resistor. You would have had, let me do this one. So you have 2 plus 4 in parallel with 3 in series with 4 in parallel with 2. All right? So this is what you would have had. I'm just gonna put letters. So let us say when you put those together, the impedance is A. The 3 together, you have 3 and A, you get B. And then 4 and 3, you get C. All right? So let me just circle those, B, C. Okay? It means, therefore, from the circuit, I mean, you can go to the circuit or you can just look at this. With V1 at the input, it means that the voltage across this portion, you'd use voltage divider between 2 and C. So you would get, let's call it V1C. Whatever is across V1C is across the 4, so it's also across everything here. So it means therefore that V1C would be across the 3 and everything beyond that. You then, because you have another plus here, voltage division again. So you are going to now have V1, I'm calling it CA. So V1 CA would be across these two resistors. If they are in parallel, it means that the voltage across the 4 ohm is the same voltage across the 2 ohm. So you will have V1C over 2 to be equal to minus I2, because I2 is the current through this resistor. So you get the voltage here based on voltage division. You get the voltage here based on voltage division. And that voltage would be the same voltage across the 4 and the 2 because they are in parallel. Once you have that, then of course, I2, so it means that Y21 would be equal to 1. Well, this component, I can't put it simpler than this. This component, which would be a fraction of V1, all right? It would be a fraction of V1 divided by 2 will give you minus I2. So whatever that fraction is, you would have V1 times that fraction over 2 is equal to minus I2. And from that, you find Y21. That is what it means that you do it from first principles. And students, as I said, you have to do it. I am not going to do this for you. So you would have found Y21, Y11, and Y21. You then make V10 and find Y12 and Y22. From that, you get your Y matrix. You do the same thing from scratch and find Z. All right? You find Z, Z11, 12, 21, 22. These are the open circuits. So again, from your circuit, you have this open circuited. And you look in here for Z1, Z11, because that links the relationship between I1 and V1. So in this instance, what you have is 2 in series with 4, which is in parallel with 7. Because whatever current comes through the 3 goes through the 4. So that gives you Z11. For I2, yes, or rather V2, the voltage here, because of course Z21, sorry, Z21 is equal to V2 over I1. So you look at I1, it is flowing here. So that's it, the plus sign. So it passes through the 2. At this point, it is now going to be divided between the 4 ohm and the 3 and the 4 in series. So you now will get a component of I1, which goes through the 4 ohm. So if quick voltage division, the current through that 4 ohm would be 4 I1 over 11. So it means, therefore, that V2, bearing in mind there's no current flowing through the 2 ohm. Therefore, V2 would be seen across the 4 ohm. So you simply multiply this by 4 in order to get V2. And so Z21 would be, what's that? 16 over 11 or something like that. That is how you're going to do it from scratch. So you then would have your Y matrix and your Z matrix. The question says that you must use the conversion matrix to verify what you have done in part A. So based on the 2 matrices that you have, you're going to invert this and check to see whether or not the values you get in the impedance matrix are correct. That is what I asked you to do. And that is what you are going to do from scratch. If you don't do it, I'm sorry to be speaking like this evening, but if you don't do it, just forget about this topic. And I'm telling you, you're going to be tested on it. So if you can't do this, just prepare for the next topic. Let's go to this one. This one is a lot more complex, right? However, what we have done is to give you a network. So you don't know what is in that network. Quite frankly, it doesn't really matter. Because the theory that we have presented so far tells you that once you have parameters for this network, you can do the analysis, regardless of what you're connecting at the input or what you have at the output. All right? So, couple of things you need to bear in mind. When we speak of V1, I2, and V1, I2, I1, V2, we're talking about, that would be, sorry. I2 is the current going in, V2 would be here. I1 would be the current at this point, and V1 is the voltage at that point. So the I1, the I2, and the V1 and the V2 are related to the network itself. So it's not out here, it is right at the port 1 and port 2 of the network. So in this example, you're given a 3 ohm load. You're told that you have a 75 volt source, and then you have this network of resistors. All right? Question is, how do we go about completing this analysis? So the parameters that you're given are the hybrid parameters. All right? You're given the hybrid parameters, and we now need to use these parameters in completing our analysis. Okay? So the hybrid parameters, as we said, it deals with input and output. So we're dealing with V1 and I2. All right? But before we get there, we have to, as I said, find an expression that links our source and these resistors to V1 and I1. And then we are going to link I2 and V2 with respect to our load. That one is always, well, I shouldn't say that. In most instances, that one is the easier to deal with. But we're gonna now look at the input and how we can do the analysis there. So in order to assist us in this analysis, I put in some currents, right? And what we are going to do is to apply, what we're going to do is to apply Kirchhoff's current law to this node. Right? So we're applying Kirchhoff's current law to that node. And if we apply the current law to this node, all we are saying is that IS is equal to IX plus I1. And I'm introducing this voltage, this node voltage Vx. All right? We're going to get rid of it. Don't worry. We're going to get rid of Vx, but we're using it to aid in our analysis. So have you put in these currents? Put in I1, V1, I2, V2, Vx, Ix, Is. You have those in place? All right, I suppose I'm talking to myself today.
Yes, sir.
Yes, sir.
So for V1 is going to be equal to Vx minus 10 I1. All right? Why? Let's look at it. If we want the voltage here. So if I know the voltage at this point, all right? Then if I find the voltage drop across the 10 ohm, I would know the voltage V1. So Vx is equal to V1, or V1 rather, is equal to Vx minus 10 I1. So that's the first equation we can write. Or Vx is equal to V1 plus 10 I1. Let's rearrange. Nothing spectacular. When I look at Vx, however, Vx, the voltage here, is going to be equal to 75 minus 5 Is. Everybody agree with that?
Yes, sir.
Yes, sir. Yes, sir. I agree.
Good.
Yes, sir.
But we need an expression for Is. Look at Is. Is is equal to the current through this 15 plus I1, as we said here. But this Ix is equal to Vx over 15. But that's not a problem because we already have Vx in terms of V1 and I1. So in that way, we are able to eliminate. Whoops. When it rains, it pours. My battery just sounded the alarm. Excuse me, I said. All right. Well, thought I had much more time on this. Okay. So from this, let's just look at the equations now. So remember we spoke about V1 with respect to Vx and I1. 75 minus 5 is, but as I said, is equal to Vx over 15 plus I1. Remember the objective is to find a relationship between V1 and I1. All right? So based on that, we can now make some substitutions. All right? So Vx, so what we have over here, we have the 75 minus Vx over 3 minus 5I1. And from that, and this is where it is complicated, I know, and I want it to be. All right? You figure that out. You figure out the reason soon. Can I move on?
Yes, sir.
Yes, sir.
Okay. So the objective here is to get an expression for Vx. So if we simplify that, 4Vx over 3, so that's just bringing this across. So we have 1 1/3, which is 4 over 3 Vx, equal to 75 minus 5I1. I cross multiply, and of course, I'll get an expression for Vx. So this is Vx. But remember earlier, we said that Vx was also equal to V1 plus 10I1. So I do that, and I can now establish a relationship between V1 and I1, which is this. Time is it? Let me know when I can proceed.
Yes, sir.
Okay. All right. So from this, we can then find V1. So we now have our expression for V1. Or you could have made it I1. It really didn't matter. So this is from the input side. So that's at the input. On the output side, V2 is equal to minus 3I2. So I now have V1, I have V2, but I have the hybrid parameters. So the next thing I need to do is to write using the hybrid parameters. There's no point in converting, right? We have the equations for the hybrid parameters, which is for V1 and I2. We have an expression here for V1, and we can write an expression for I2. So what we now have, making the substitutions, this is V1. That's H11. That's H12. This is H22, H21, and this is I2. So from having the hybrid parameters I put into this equation, and we solve, what were we asked for again? All right, so we're asked for the output voltage V2, which is the reason I didn't make the substitution for V2. All right, I substituted for I2 instead. So it means that we are left with V2 in the expression. So solve for V2, which of course would be equal to V0. And in part, this is what two-port networks is all about. Now, you're here. You have a choice. You have a choice. Here's the choice. You can put on your notebooks until Wednesday next week, or you can review every solitary thing that we have spoken about on two-port networks. You can do redo these exercises through to completion, or you can ignore them. One thing I'm going to guarantee you is that if you should ignore them, then come next class, you'll be totally lost. And I'm going to take a very hard line. It is absolutely important. Oh, I almost gave away 5%. I forgot my declaration. But the choice is yours, all right? That's it from me for today. Could have been a little more impactful if you had just done the work. I'm not interested in whether or not you get it right, you know. What I'm interested in is your willingness to make an attempt. So at least I can hear and figure out where you're going wrong. I can't make that assessment if you just sit and wait for class.
Sir.
Yes, sir.
Yes, sir. I attempted it and all that, sir. But,
Sir, I attempted also.
one question, sir. It's from the first question. There was I was wondering if an expression could not have been made for the if you just go back on the first circuit, sir. No, sorry, the first one. Sorry, it is the second one actually. Sorry, the second circuit. No, yeah, after that. The other circuit, the one after that.
The what?
The circuit after this one, sir. Where you have the yeah. I was thinking if an expression for V1 wouldn't be V1 couldn't be equal to minus 2I1. That was what I was thinking at one point.
Go again?
I was thinking that V1 could be equal to minus 2I1. That expression would be incorrect.
You mean this V1 here?
Yeah.
Being equal to 2 times this?
Yeah, minus 2I1, yeah.
Why would you even think that?
Well, I was thinking that the V1 would be the same across the 4 ohm, which would, at that point where you have the circle.
Yeah, but Mr. Atkins, think about it. If you have a current passing through a resistor, what's going to happen?
I have a voltage drop. Yes.
So if you start at V1, the voltage here is much smaller.
Yes.
Huh?
That would be true, yeah. But
What? There's no but. And the voltage here would be smaller also. Because you have another voltage drop right here, so.
okay, so all right.
You agree?
Yes, I agree. I agree about voltage dropping. It's just that I was all right, you have your terminal and V1 at the terminal right at the end here, right? So that voltage. All right, I was also thinking also that maybe I was thinking about splitting up the circuit and having like a pi network, which I was thinking that no, that wouldn't make it because they would leave out the 2 ohm resistance. Right? I was also thinking that seeing that it's being relatively symmetrical, that Y11 and Y22 would be equal from during the admittance. I didn't find any admittance.
Well, that's the whole purpose for me saying you must do it what?
First principle.
If you do that, then you begin to identify certain things about two-port networks. You cannot sit down and look at these things and learn it.
Oh, no, sir, I did it about it, just that I was wrong. I did
So I want you to focus on this. And when I say first principles, it means therefore that you're going to go back. You're going to go back all the way up here, sir. You're going to go back all the way here, sir. Start with that.
Yes, sir. I started nothing about I just made some grave errors.
Come back, listen. All right.
I thought it was my equation, the first thing, admittance and the Z parameters. But, you know,
But as I said, unless you do it, you're not going to be able to see certain things that I needed to discover for yourself. So when you discover it, then we can talk about how we treat with it otherwise. But you have to discover it.
You have to do it and is it correct?
Right? Isabel and whatever the king's name was, they remained in Spain and Columbus same come out and discover. But anyway, you have to discover it. All right, that's it for me for tonight. See you all Wednesday. All things being equal.
Yes, sir.
All right, good.